In this video, we're going to address the question, when can an irreducible polynomial have multiple roots? When I say multiple roots, I don't mean when can it have more than one root. What I mean is when can an irreducible have roots of multiplicity more than one in an appropriate field extension? Roots with multiplicity greater than 1. Just to give a little bit of context and motivation, I want to give an example. So let's take the irreducible polynomial x squared minus 5 over q. So as a polynomial in q adjoint x. This is irreducible because it satisfies Eisenstein's criterion for p equals 5. And we know how to factor it in an appropriate extension. It's x minus root 5, x plus root 5, which I'm going to rewrite as x minus root 5 times x minus negative root 5. And the reason I want to write it that way is that most readily reveals the roots of this polynomial, root 5 and negative root 5. Notice those are different. We like it when that happens. When that happens, these two roots, if they're roots of the same irreducible polynomial over q, or over some base field, these are called conjugates over q. So one thing that we notice is that those are two different numbers. And if we take some other irreducible polynomial over a base field and factor it completely, that is split it, in an extension field, we wonder when it might happen that we have a full complement of conjugates, that is a whole bunch of different conjugates with no repeats, and when we might actually have repeats, that is when we might have factors that are equal to one another and therefore have a root of multiplicity more than 1. So that's what we're interested in. So in this video, we're mainly going to address this question in fields of characteristic 0, but we'll also talk about what happens in a field of characteristic p, where p is a prime. So let's take the case in which f, our base field, has characteristic 0. All right, and let's suppose f of x is irreducible over f. All right, so the question is, can f of x have multiple roots? In an extension E. Well, now by the theorem that we've proven, for this to happen, f of x and its derivate, df of x, must have a common factor of positive degree. And furthermore, they must have one in f adjoint x. That is, we should be able to find one without even going into the extension field E. All right, so for that to happen, f of x and df of x have to have a common factor. Okay, but wait a minute. Wait. So wait a minute. Notice what I just said about f of x. F of x is irreducible. So wait, how could this possibly happen? Because if f of x and its derivative are going to have a common factor of positive degree, then that means, well, okay, if there is some g of x belonging to f adjoint x with degree of g of x greater than 0, such that g of x divides f of x and g of x divides the derivative, then, well, using the fact that g of x divides f of x, that means f of x has to equal g of x times h of x for some h of x belonging to f adjoint x. And then g of x or h of x has to be a unit. G of x can't be a unit because its degree is greater than 0, so h of x has to be a unit. All right, so that means h of x is a unit, its degree is 0. So the degree of g of x has to equal the degree of f of x. That's going to be a major problem for us because we also said g of x divides the derivative of f of x. And the derivative of f of x, its degree, is equal to n minus 1, where n is the degree of f of x, where n is the degree of f of x. So now we've got a problem here. So g of x can't divide d of f of x, and so we have a contradiction. So what this means is that we actually can't run into this scenario with an irreducible polynomial in a field of characteristic 0. So that's the moral here. Moral is, in characteristic 0, an irreducible polynomial never has multiple roots. Never has roots of multiplicity more than 1. There we go, multiplicity greater than 1. Never happens. And in fact, you may wonder, what in the world about this argument used the fact that we were in characteristic 0? I never actually explicitly pulled this in. So I'm going to set up another spot here to work, and then in the meantime you can think about where I might have been very sneakily using the fact that we're in characteristic 0. It's subtle. You may even want to pause the video and see if you can find it. There actually is a place in this argument that assumes that our field has characteristic 0, but it's not at all obvious. It's not going to leap out at you. Okay, so the question is, what in the world would be different about characteristic something other than 0? Like, why would you even think of splitting the argument up this way? At this point, I haven't defended that at all. So in characteristic P, well, let me just give a motivating example here that might illustrate where we could have a problem. So as an example, let's put ourselves in Z mod 5 adjoin x. So that's characteristic 5. And let's consider the polynomial f of x equals 2x to the 10th plus 3x to the 5th plus 1. All right, that is a polynomial in Z mod 5 adjoin x. What is its derivative? Well, the derivative of f of x in this case is going to be 10 times 2 times x to the 9th. That's 20x to the 9th, but that's really 0. That's 0x to the 9th. I'll put the x to the 9th there just to be a good sport, but that's really 0. And then 3 times 5x to the 4th, that's 15x to the 4th, but really that's the same as 0x to the 4th. And then, of course, the constant 1 just goes away. So the derivative of f of x is actually just the 0 polynomial. It does not have degree n minus 1 as we promised in the previous argument. So in the previous argument, we were able to blithely say the derivative of f of x has degree n minus 1, where n is the degree of f of x, because when we take that top degree term and take its derivative, we're dropping the exponent by 1, and we're multiplying the original exponent by the existing coefficient, but none of that process is going to produce a 0. But in characteristic P, that process absolutely could produce a 0. And just to point out a little technical, I don't know, it's not really a glitch, it's just a technical nuance of what's going on here. This exponent should be interpreted as an integer, not an integer mod 5, just a regular old integer. X to the 10th is different from x to the 5th in Z mod 5 adjoin x. So you may wonder, well, when we take the derivative, how can we multiply something that's in Z mod 5 by an integer? But this is the type of multiplication we talked about at the very beginning of the semester, where it's not really multiplying two things in the ring sense, it's repeated addition. So this 0 here is really 2 added to itself in Z mod 5 10 times. So that's why we can do something like that. But yeah, this really throws this argument here out of whack. I mean, it's fine for characteristic 0, but in characteristic P, something very different could happen. But you'll notice that what happened here, it required kind of a miracle to occur. We needed this x to the 10th to have an exponent which was divisible by 5. We needed this x to the 5th to have an exponent that was a multiple of 5. And then we could have a constant term here, but that's really just 1 times x to the 0. So what this took was this needed a polynomial of the form f of x equals g, some polynomial function of x to the p, where in this case p was 5. So in this case, f of x was 2x to the 10th plus 3x to the 5th plus 1. So our g could be thought of as g of x equals 2x squared plus 3x plus 1, and then for x we're really substituting x to the 5th. So that's what it took for us to get into trouble. And even then, just as a spoiler here, this polynomial actually won't be irreducible over z mod 5. This particular one won't be irreducible because it has a root. It has a root of x equals 4, which is -1 in z mod 5. But I'm doing this to illustrate why this argument here may go amok when we're in a characteristic p, where p is a prime. Okay, so moral of the story is, if we have an irreducible in a field of characteristic 0, then that's it. It's not going to have any roots of multiplicity greater than 1, even in an extension field. But in characteristic p, something hinky could happen. And we're actually going to find that it takes some specialized circumstances for that to occur, but it could happen if we have a polynomial of the form f of x, a polynomial function of x to the p, where p is the characteristic. And you can actually show on your own that, first of all, having a polynomial of this form always gives you a derivate of 0, which means that the original f of x and the derivate will have a common factor, but also that's the only way that this feature can occur. Otherwise, you will have a derivate that's non-zero, even though it may not have exactly degree n-1, and then you can resort to some version of this argument here, because what was really important was we ended up with a derivate that was non-zero and of smaller degree than the original f of x, which means it's not going to be able to have f of x as a divisor. F of x has larger degree. So anyway, the main moral to take away is that irreducible polynomials over fields of characteristic 0 never have multiple roots. They will have a full complement of distinct roots in the appropriate extension field.